Okay, for this video, we're going to talk about logical equivalencies. This is the second video for Module 1 in this class, and we're still on textbook section 2.1. So I want to talk about logical equivalencies, but I'm going to start a little bit with some vocabulary, two vocabulary terms we need to talk about, tautologies and contradictions. And a tautology is a statement form that is always true, regardless of the truth values for the individual statement. So, for example, if we have a truth table where we've got our inputs and our output, I don't know what the inputs are, but I know the output will always be true. Every time. So this is a tautology. And a statement whose form is a tautology is called a tautological statement. So can we think of any examples of a tautological statement? Well, there are lots of them out there, but a common one is P or not P, right? And if we do a quick truth table of this, we have P, we have not P, and we have P or not P. We can see that while these statements, P is either true or false, we only have one variable, so those are the only choices. And not P is going to be the opposite, so false and true. Now, if we OR the two together, true or false is true, and false or true is true. So you can see that no matter what the inputs are, the output is always going to be true. And that is a tautological statement. So this is a tautological statement. So a contradiction is very similar to a tautological statement, except it's a statement that will always be false. So an example is, again, if we have our truth table with inputs and outputs, don't care what the inputs are, this is always going to be false. This is a contradiction. And again, a statement whose form is a contradiction is known as a contradictory statement. So what's an example of a contradictory statement? Actually, that should be e.g., shouldn't it? Should be doing that. Example, well, how about P and not P? So it's very similar to our last one. Except here, if we do the truth table, we have true or false. Not P is again the opposite. And now we AND these two columns together. And in both situations, this is going to give us false, because both sides have to be true for an AND to be true. So this is a contradiction, and this is a contradictory statement. Right? So this is a truth table of a contradiction, and this statement right here is called a contradictory statement. And these terms, a tautology and a contradiction, are going to come in useful when we get to our tables of logical equivalency. So, what does it mean for two statement forms, P and Q, to be logically equivalent? This is how we write it. And notice this is not an equal sign. It has 3 lines, and that's because equivalence is not the same as equals. So I can have two statements, dogs eat mice and cats bark, and cats bark and dogs eat mice that are equivalent to one another, but they're not exactly the same. They are not equal, right? This one starts with the word dogs. This one starts with the word cats. So these are not equal to one another, but they are equivalent to one another. Both of them say that dogs eat mice, and they also say that cats bark. So they're saying the same thing, but they're not identical, so they are not equal to one another. These statements are logically equivalent to one another. Right? And one way of knowing that two statements are logically equivalent is that if they have identical truth tables, and this is the output portion of the truth table. So if the truth table output is the same for both, then we say these are logically equivalent. So let's do an example. I'm going to prove that not P and Q is equivalent to not P or not Q. So I've left this blank. Let's figure out what these columns should be. I'm going to grab just this first part in here to go in the first column. And then I'm going to add that negation in for the second column. And similarly, over here, I'm going to isolate not P and not Q. And then I'm going to combine them with that or. So let's fill this out. Okay, and them together, we get true, false, false, false. And then we have the opposite. We take the opposite. So this is false, true, true, true. And then let's take the negation of P. That's going to be false, false, true, true. And the negation of Q, which is going to be false, true, false, true. Now, if we OR these last two columns together, we're going to get false, say one thing and write another. We're going to get false, true, true, true. So, the goal here was to prove this. Have we proved it? Absolutely not. Not yet. Right? We need to use the definition. What does it mean to be equivalent? Well, here is the left-hand side of our equation. And here is the right-hand side of our equation. And we look at them and notice that they're all the same. Well, if you remember, a proof is a convincing story. If I just showed you on paper, if I just showed you this truth table right here, as given, are you convinced that they're equivalent? Well, no, we need a little bit more of the story. So I'm going to add that since the two truth tables associated with the two sides of the equivalency are identical, we know the two sides of the equation are equivalent. Okay, so you don't want to forget that a proof is a story. Here's the story. And it's using the truth table, so I should have said that. This is the story. But you need words in a story too. Also, this entire thing is often called a truth table. So this whole thing is known as a truth table. But when we talk about the truth table of a statement, this is often what we are referring to. An even easier or more obvious logically equivalent form could be not P is equivalent to P. Right? Just like in algebra, the negation signs cancel it out. If P was true, the not P is false, and not P is true again. So I will leave the truth table for this up to you as an exercise. So let's talk about logical equivalences. There's a whole list of laws of logical equivalencies that somebody else has already come and sat down and demonstrated with truth tables and demonstrated with proofs. And so now we can just use them just like we use the rules of algebra. And in fact, a lot of these are similar. So the commutative laws just say that the order can change. So P and Q is the same as Q and P, or is equivalent. And we have the conjunctive form, which deals with the and side, and the disjunctive form, which deals with ors. And so P or Q is also equivalent to Q or P. Another law is called the associative law, and that says if we have all the same symbols, so here we have two ands, we can change the parentheses around however we want. Here we have two ors. We can change the parentheses around however we want. We can group them in whatever way we wish. Sort of like if you had algebra and you had 5 plus 4 plus 3, we could group it that way, or we could group it that way. Okay, so those are the associative laws. Now, if the signs are different, so here we have an and an or, the associative laws do not apply anymore, and instead this is known as the distributive laws. And effectively what we're doing is we're pulling this P and we're putting it in front of each of the terms in our other form. Right, so we're distributing the P and. This is an analogy in algebra is if we have 5 times 3 plus 2. Yes, technically we could just add those together first, but an alternative is to say 5 times 3 plus 5 times 2. Right? We're distributing the 5. So, and again, there's a conjunctive form for this and a disjunctive form for this. Identity laws. If we and anything with a tautology, that's what that T means. This is a tautology. We're going to get the original thing. And that makes sense, right? If we have P and a tautology, well, the tautology is always going to be true. P is going to be true or false. And if we and them together, we're going to get P again. And them together, so this is P and T. And this first row is going to be true, and the second row is going to be false. And these two columns are the same. Similarly, if we or with a contradiction, we're going to get P as well, but I'm going to leave the truth table for that up to you. Next laws, the negation laws. This is one we already saw when I was demonstrating the definition for tautology. We used this example. P or not P is always true, and P and not P is always false. Double negative law, we also briefly talked about that. If you have two negatives, that is equivalent to having no negatives. They cancel out, and there is no, this isn't really conjunctive form or disjunctive form. There's just one form of the double negative law. Idempotent laws. This is saying if you have P and you and it with yourself, you're going to get P. And if you have P and you or it with yourself, you're going to have P. So pretty straightforward. Universal bound laws. If we or with a tautology, we're going to get a tautology. So before we anded with a tautology and we got P. Here, if we or with a tautology, let's think about this. If we have P and a tautology and P or that tautology in a truth table, this is going to be all true, and this is going to be true or false. And since it's or, if either side of them is true, it's true. So that follows naturally. And similarly with anding with a contradiction. De Morgan's laws are a little tricky. This is where a lot of students get stuck. A lot of people get confused. These actually turn up all the time when you're writing a program. Anytime you try to negate something, so here we're negating an and, we're going to get two negations and an or. So when we distribute that negative sign, this is different than in algebra. When we distribute that negative sign, it switches the operator. And this happens in both scenarios. So if you try to negate an or, it's going to switch to an and. And we're going to prove this one or demonstrate it here in a few minutes. So I believe, no, actually I don't. We're not going to do that. We may have done that in the last video. I don't remember. But this is a very important one to get familiar with, De Morgan's laws. We have absorption laws. P or P and Q is P. And P or Q is P. I'm going to leave the truth tables up to you to do those, to convince yourself. And we also have the negations of tautologies and contradictions. The opposite of tautology is a contradiction, and vice versa, which should make sense. Okay, what if we want to prove something new? I want to prove this equivalency. Well, there's a couple of ways I can do it. I could do a truth table, like we did before, and demonstrate that the truth table for this side of the equation and the one for this side of the equation are the same. Write up a little explanation, and that would be a proof that these are equivalent. But there's another way of proving this. We can do what's called an algebraic proof. Which in many ways is simpler. And what this is going to do is this uses the laws of equivalency that we saw on the previous slides. So we're going to do it that way. So I'm going to start with one side of the equation. And this is really important. It's a common mistake people make to start with this whole thing and then try to simplify it down. Because the problem is we are trying to prove this equivalency. I am not trying to illustrate it. I am trying to prove it. And we'll see later in the semester that there's actually logical mistakes you can make if you just sort of start with this and work down where you're manipulating both sides at the same time. You can prove false things that way. So this is not a logically valid way of proving this problem. Instead, we want to pick one side of the equation. I'm going to pick this side and try to make it look like the other side using the laws of equivalency. So let's start. I'm going to start with negation of P and Q and P or Q. And I'm going to say, okay, using the laws of equivalency, what do I know about this? Well, I see that there is a negative sign here, right? This negative sign that could be distributed into that equation. So I'm going to distribute it using De Morgan's law. And what this comes out to, remember we have to flip the sign. This other half I'm going to leave alone. Now I'm not having a lot of space, but this is going to be, you want to specify this is via De Morgan's law. Okay. So this underlined red part over here is going to have transformed into that by De Morgan's law. And now, over here, I'm spotting a double negative. So let's deal with that. So I'm going to say this is equal to P, or let me move this up a little bit. P or not Q, and P, and this really should be in parentheses, or P or Q, or and P or Q, like that. So here, I have converted that double negative into a single positive, and this is using the double negative law. Okay, now let's look at this equation and see if there's anything useful we can do. Well, I'm going to notice that this P, let me see if I can undo that, that this P or and this P or are matched with an and. This is actually the distributive law backwards. Right, so another way of writing this is to say P or negative Q and Q. So remember we said with, and this is by, so here's the P or now. This is by the distributive law. It's just sort of been done in backwards. So normally we do it the other way. Here we're doing it this way. And again, it only works because we had ors and an and. Okay, so let's take a look at this now. And now I'm noticing that this is a contradiction. So I can rewrite this statement as P or contradiction, and this is by the negation law. And finally, this whole thing is equal to P by the identity law. Right. And this is what we were trying to prove. So, by starting with our original statement and taking one step after another that is justified by one of these laws, right? You have to justify it by these laws. We can get to the other side of our equation, and this is known as an algebraic proof.